Hello guys, so welcome to the DSP lectures, and we are continuing our discussion on filter realization, and today we'll see that how IIR filter are realized using direct form 1. So as mentioned earlier, for the first lecture we have seen that direct form and linear phase realization of FIR filter. Now in today's lecture this will be the 2a, lecture number 2a, and here we'll be exploring at how direct form 1 realization is done for IIR filters. So as we know that IIR filter can be realized in two ways: direct form 1 realization and direct form 2 realization. Now recursive realization of IIR filter is possible if in this case the output, current output, that is present output y of n, is basically a function of past outputs, past and present inputs. So we can say that y of n is a function of past outputs. That means y of n minus, say, capital N, you can say, and current output x of n, and current input, so past input, say x of n minus m. So this kind of thing we should get, and this form corresponds to an IIR digital filter. So let us explore this recursive realization. So IIR filter can be realized using recursive manner. So if we see these relations, let us consider that this particular difference equation represents the IIR filter. So this particular difference equation, so here what we have done, this is our present output, these are the past output, and here we have the present and past both inputs. So if we are taking this to the right hand side, then we can represent the present output, okay, so I am writing PR for present output as a function of past output and present and past input. So if we expand this equation, we are getting minus a1 y of n minus 1 minus a2 y of n minus 2 and up to minus an y of n minus capital N. So up to this, suppose we have the values of past output. Similarly, b naught x of n is my present input. Here I am writing for the present, so this is my present input, and here all I have the past inputs. So here we have the past outputs, here we have the present output. So present output is a function of past output, present input and past input. Now let us define another polynomial w of n, which is basically the present and past input. So w of n is equal to b naught x of n b1 x1 of x of n minus 1 up to bm x of n minus m. So this is what we are defining, a different polynomial w of n, and using this w of n concept, equation 1, that means this equation can be written as y of n is a function of the past outputs and w. So in this way we are representing it. So now let us try to realize one by one. So this equation w of n, which is b naught x of n b1 x of n minus 1 and up to bm x of n minus m. So x of n here I am getting, and here I have a multiplication factor, so b naught I am using, then I am using a delay element z inverse. So at this particular point I am getting x of n minus 1, So x of n minus 1 is having the coefficient b1, so that is getting added up. So here we are adding up all. Then another delay element, so at this point we are getting x of n minus 2, coefficient is b2, and adding up, so up to x of n minus m. So these many delay elements we will have to use, whereas these many multipliers also we have to use. Then finally we are adding them up, so as the output we are getting w of n. So please have a look here in equation 2. W of n is the output. You can say this is intermediate output, and this is x of n is the input. Now if we have a look at the equation 3, then we find y of n is the output and input is w of n, whereas y of n minus 1, y of n minus 2, all these things are the feedback. So this is forming a feedback loop. So feedback, okay, and here this is the input for finding y of n. If we analyze this particular equation, not the filter, only for this equation, so w of n we are giving here, and we are getting y of n as the output, and we are taking back this output. So feedback we are providing. So at this point we are getting y of n minus 1, that is the past output, y of n minus 2 up to y of n minus n. So all past outputs. So n number of delay elements will be using, and here we have the multiplier or for the coefficient. So these are representing the weights. So minus a1, minus a2. So whatever we have weight over here. So that's thing we are putting, and we are adding them up. So along with this w of n, all these things are added up, and we are getting y of n. So now if we combine both this equation 2 realization and equation 3 realization together, then we are getting this as the entire realization of the IIR filter, and this form of realization is called direct form 1 realization. Now let us take a small example. Say we are given this difference equation. So this is characterizing one IIR filter. So y of n, that is equal to 2r cos omega naught y of n minus 1 minus r square y of n minus 2 plus x of n minus r cos omega naught x of n minus 1. So don't get afraid of these terms. These are just the coefficients. So if we have the value of omega naught and r, we can find some numerical value. Just like in IIR filter realization, we have used some numerical value. So here also you can have some numerical values, or this kind of tricky questions also you may get. So here, just as before, whatever we have discussed, we are defining w of n as the intermediate signal, so which is consisting of the present input and past input, and y of n, hence you can write as function of past outputs and w of n. So now if we realize them separately, equation 1 let us first realize. So this is the realization of equation 1. So here we have x of n and we have x of n minus 1. So only one delay element we have to use, and here we have x of n minus 1. So what are the weights associated with this? X of n is having weight 1, so we are writing 1. Even if we do not write this thing, by default it will mean it is 1. And here we have this as the weight minus r cos omega naught. So minus r cos omega naught, this is the weight only. Similarly, if we try to realize equation 2, so here we have w of n as our input. So we have written w of n here, and from y of n we are taking the feedback. So this is forming a feedback path. So z inverse 2 delay element we are using. At this point we are getting y of n minus 1, and here we are getting y of n minus 2. So here you can see n minus 1 and n minus 2. Two past outputs we are having, and then we are adding them up. So W of n is getting added with this and producing Y of n, that is our current output. So the last step, we should combine them together. So after combining this, the entire filter structure will look like this. So now many questions you may get, instead of these values you may get some numerical values, or somewhere R value will be given, omega naught value will be given. So let us consider R equal to say 0.25 and omega naught equal to say 0.45. So omega naught is the digital frequency. So I am leaving it to you. Use these values and find some numerical numbers. Try it with other values, say R equal to 0.1, omega naught equal to say 0.3. So this kind of values you can put, and you can see that how the weights are changing, filter coefficients are changing. Okay, so here we end today's discussion. Next discussion will be discussing about the direct form 2 realization of IIR filter. So these are the references. So thank you very much for joining, and join me for the next part, lecture 2b. So where we will be discussing about the IIR filter structure using direct form 2.